Welcome to this presentation about ray tracing in Unity using the High Definition Render Pipeline, or HDRP for short. Hopefully, after watching this session, you will have a much better understanding of the key ray tracing features of HDRP, and you should be able to greatly increase the visual quality in your visualization and even real-time games. My name is Pierre-Yves Donzala. I'm a technical art manager at Unity, and I specialize in lighting, rendering, UX, and tools design for art workflows. I worked in the AAA game industry as a lighting artist for more than a decade, on productions such as the Crysis franchise, Grand Theft Auto, and Red Dead Redemption. My colleague Anis Benyoub, senior graphics engineer at Unity, is currently working on the ray tracing pipeline for HDRP. He will be available later at the end of this session to answer your most technical questions. In this webinar, I'm going to show you how to install Unity and navigate the project settings and how to set up HDRP for ray tracing with just one click using the dedicated wizard. I'll let you know how to use the volume system in HDRP to set up all its effects, including ray tracing ones. I'll then show you how to use the Raytrace Ambient Occlusion and how it can bring great visual improvements on the cheap. We'll see why Raytrace Reflections are so much better than rasterized screen space ones. I'm going to play with mirrors. Then I'll explain to you how to enable the Raytrace Global Illumination for real-time lighting propagation, and how to use the different debug views to understand how the denoiser works. I'll show you how great the Raytrace Shadows are in HDRP, and how to even create semi-transparent colored shadows in just 3 clicks. We'll have some fun with a car to showcase the power of all these effects at once, and we'll end the session with path tracing in HDRP, the unified solution to get top lighting with no compromise. The level I'm going to use for this session is a brand new scene template designed to showcase important concepts used in HDRP, like the physically correct lighting and the realistic exposure. This template is available with Unity 2020.2. The first room is a circular arena with a large concrete platform. It's perfect to test assets in a low noise environment. Then, the second room is an interior that features mostly indirect lighting. In the tree cage, you'll find many advanced materials with transparency, subsurface scattering, and tessellation. This is a great showcase for the GPU light mapper and the local volumetric fog in HDRP. Finally, the last room features a minimalist living space with several real-time lights and emissive lighting. Again, all the lights and camera exposure settings use real-world values. So it is a great example if you want to achieve photorealistic results in Unity for your visualizations and games. And in the next 30 minutes, I'm going to convert this level to use the ray tracing effects offered by HDRP. First, let's see how you can download and install Unity. Search for Download Unity on your favorite search engine. Once you're on the official Unity webpage, you can then download the Unity Hub. So the Hub is a program that will let you download different versions of Unity. It will also let you manage your projects, learn about Unity with fun tutorials, and access the community channels. Head to the Installs tab and pick one of the latest official releases. Once the download is complete, head to the Projects tab and create a new project using the appropriate Unity version. Pick the HDRP template, give it a sensible name, and hit the Create button. The very first time you load the project, it will take a couple of minutes for the editors to start, because it will compile all the assets, scripts, and shaders in the project. But don't worry, the next time you will start Unity, it will just take a few seconds to open the editor. Now let's see how you can activate ray tracing. I'll open the project settings in the Edit menu to look at my quality settings. I've already created low, medium, and high, but these don't actually use ray tracing. By the way, you can see that each quality level has an HDRP asset assigned to it. It's a file on disk that stores all the HDRP settings per quality level. For this ray tracing presentation, I'll actually create a brand new quality level dedicated to ray tracing. I need to assign an HDRP asset to it, and for that, I'll simply clone an existing one and rename it accordingly. Then, I just assign it to the quality level I just created previously. With this new HDRP asset selected, you can see that if I try to enable the ray tracing features in my project, a warning is displayed. We actually have a one-click solution to fix this. It's called the HDRP wizard. Once it's opened, head to the tab named HDRP plus DXR. You will see that some features are not active, such as DirectX 12 for instance, which is needed for ray tracing. Simply click the Fix All button and Unity will take care of setting up your project correctly. It might ask you to restart at some point to finalize some of these changes. So before we start talking about ray tracing features, it's important that you understand that many effects in real-time graphics these days rely on the results of previous frames. This is usually called temporal accumulation, and it's required to provide good visuals at an acceptable frame rate. Therefore, it is important that you activate the temporal anti-aliasing, usually called TAA, on your scene camera. It's a post-processing effect that greatly reduces aliasing in your scene, and it uses motion vectors to deal with moving pixels on screen, typically when the camera or object move. For the TAA to work correctly in the scene view, you also need to make sure that Unity refreshes the scene constantly by enabling the Always Refresh function in the scene toolbar. And of course, for your actual game camera, you'll also need to enable TAA to take advantage of the temporal reconstruction, which will minimize noise artifacts between each consecutive frame. Now it is time to enable the ray tracing features in our HDRP asset. In the project settings, head to the HDRP quality settings and select the HDRP asset that you want to tune. In our case, it's the one assigned to the ray tracing quality level that I created a couple of minutes ago. First, make sure the ray tracing is actually enabled. Then activate screen space ambient occlusion, global illumination, and reflections, including transparent. To take advantage of the Raytrace Shadows for the sunlight and the local lights, we will also activate the screen space shadows. As a precaution, head to the HDRP default settings, and for the cameras, ensure that the effects we activated previously can be rendered. Alternatively, you can also select your game cameras, and in its custom frame settings, you can decide exactly what this camera may or may not render, such as shadows, transparent objects, subsurface scattering, etc. It's time to talk about the volume framework in HDRP, because this is the system that will let us tune the ray tracing in the scene. Our level is made of 3 rooms, each of them might require different HDRP settings. For instance, dark interior will require specific exposure values. For settings that should be assigned to the entire world, I use a global volume, which means it has infinite bounds and covers the whole world, no matter where the camera is located. Usually, the global volume will contain settings that are constant no matter the location of the camera in the world, and this can be the sky and the tone mapping settings, as well as the typical camera and lens effects like motion blur, grain, and vignette. Then, for each room, I have a dedicated volume that handles the exposure, the white balance, and the fog. For practice, let's create a volume in our scene that will reduce the saturation when the camera enters it. Let's add a box volume and place it in the center of the arena. We can use the collider handles to set its size very quickly. In this example, I want to keep the mode of the volume to local, because I don't want the effect assigned to this volume to pollute the entire world. To add overrides to this local volume, I need to create a profile. It's actually a file on disk that will contain the HDRP settings that we want to override. In that case, the override I want to tune is called Color Adjustments. Let's set the saturation to the lowest value, and as you can see, when the camera enters the volume, the saturation will change. Of course, if the transition is too harsh, you can as well increase the blend distance to smoothen the transition in and out of the volume. We're going to use the exact same mechanism to tweak the ray tracing in our project. This means you can easily assign different ray tracing settings to certain parts of your level. The key volume overrides we'll play with will be Ambient Occlusion, Reflections, and Global Illumination. Also, you can always hit the Help button that will open the official documentation for the volumes in case you need more information about them. The first ray trace effect we'll look into is Ambient Occlusion, or AO for short. The global volume in this scene already contains an Ambient Occlusion override actually. However, it is currently using the old-school rasterize technique instead. To activate the ray tracing, simply enable the dedicated checkbox and voila, you now have ray traced AO. Usually, AO is a fairly subtle effect, so to showcase it more easily, I'll enable the screen space AO debug view. Head to Window, Render Pipeline, and then open the debug window. In the Lighting tab, you'll now activate the full screen debug view for this effect. If you notice some jittering in these debug views, this is perfectly normal, as the temporal anti-aliasing is not applied to them. Let's revert back to rasterized screen space ambient occlusion, a technique that's been used in-game for more than a decade. The main problem with this technique is that it can only rely on the information in the depth buffer, which means that as soon as an object leaves the frame, this object won't be able to generate any occlusion at all. For instance, when the tree cage leaves the screen, it can't generate any occlusion on the floor. By contrast, the ray-traced AO can shoot rays further away than what's visible on the screen. This way, objects outside the screen can cause occlusion inside the frame, which yields to much better ambient occlusion. Let's have a look at the available parameters. Obviously, the intensity lets you increase the darkening provided by the effect. You'll probably want to keep this fairly low, as it can quickly produce artificially dark indirect lighting. Then, the layer mask system allows you to specify which objects will contribute to the ambient occlusion. For instance, let's place the vegetation in a layer called Ignore Raycast. By removing this layer from the AO pass, you are able to prevent the vegetation from contributing to the scene's AO. You can use this layer system to increase performance or for an artistic or design reason. Next is max ray length, which lets you specify how long in meters rays can travel in your scene. The longer the rays, the more likely they will hit a surface, and therefore the darker the AO will be. If you already have a good light bake, for instance, you might want to keep the ray length fairly low to only capture micro occlusion that the light mapper wasn't able to generate. Then, the sample count can be increased as well, in order to reduce the noise in the signal and facilitate the work of the denoiser. Obviously, without denoising, you can see how unstable the image is, because the samples are randomly generated between frames. This is why using the denoiser as well as the temporal anti-aliasing is so important. Let's move to the third room. You can see that the ray-traced AO is particularly effective at providing great specular occlusion, noticeably in dark areas and on metallic surfaces. It is also very evident under the chair and inside the plant pot. Before we can talk about Raytrace Reflections and global illumination in Unity, we need to talk about the light cluster built around the camera. To visualize the cluster, I'll head to the debug window, and inside the lighting tab, I'll activate the light cluster debug mode. So it is a world-aligned structure that lists the local lights and the reflection probes surrounding the camera, and this structure is used by the ray tracing to indicate what is the local lighting wherever a ray hits a surface. As I change the range of the camera cluster, it becomes a lot easier to understand how this structure works. You'd want to minimize the range, by the way, for performance reasons. You can see that certain cells are green, others are red. The red cells indicate that they contain a number of light or reflection probes that exceeds a certain limit. This means the pixel on screen that belong to those cells cannot be shaded correctly, as they will be missing certain lights or reflection probes. And this might result in light leaking potentially. So to fix that, we need to increase the limit per cell in the HDRP asset. Again, you should try to minimize this value for performance reasons. Let's have a look at Raytrace Reflections now. Again, let's use a volume override. If you disable the effect completely, Unity will only rely on the reflection probes in the scene. If I turn off all the local reflection probes, Unity will then fall back to the reflection of the skybox itself. Obviously, the sky reflection is very intense. That's why it's so important to place local reflection probes in the scene to avoid any light leaking. By default, the screen space reflection effect will use the rasterization technique, which only relies on information in the frame. For example, as soon as the Unity ball leaves the frame, it won't be reflected anymore in the puddle. Obviously, this kind of effect is rarely wanted, and in general, screen space reflections have many detractors. However, they worked with dynamic objects, and they are also very cheap compared to real-time reflection probes or ray trace reflections. For instance, racing games are great candidates for this technique, especially because the pitch of the camera will be locked most of the time. By the way, in case you notice certain reflections aren't bright enough, you can increase the maximum intensity returned by the rays. However, this might increase the noise in the reflections. Two important parameters are related to the material smoothness. They define how smooth a material can be before it can receive screen space and ray trace reflections. So, for real-time application, you should try to keep this value as high as possible to maximize performance. Here, I'm still using the rasterized technique, and you can see that the reflection of the pillars will disappear when I look at the floor. So let's activate the ray trace reflections to get near perfect results. For now, we'll stick to the performance mode that only supports one bounce, and we'll cover the quality mode in a bit. One important parameter is the max ray length. Obviously, you need to ensure that the rays are long enough to hit a surface. Otherwise, you might get light leaking. Let's turn off the denoising for a few seconds, for you to understand how the samples are distributed. To improve performance, you can also choose to cast one ray for every 4 pixels in the frame instead of 1 per pixel. It will obviously increase the noise, therefore you should keep the denoiser on and tune the filtering radius to achieve decent results. As for the ambient occlusion, you can prevent specific layer masks from being used in the ray-traced reflections. In this example, I'll disable the reflection for the plants in the cage. You can use this for artistic or design reasons, as well as to increase performance. So it wouldn't be a ray tracing presentation without mirrors. So I've prepared a mirror material with a red tint to make it easier to distinguish between the scene and what's being reflected in the mirrors. In addition, make sure the materials in your scene are set to receive SSR and SSGI. Also, we're going to use the quality mode now. It will let me increase the number of bounces to get more accurate reflections. Just for comparison, let's turn off the screen space reflection altogether. You can see that the mirrors still reflect the world. That's because I do have a few baked reflection probes in this arena. Let's turn on screen space reflection for a laugh. That's clearly the worst case scenario for this rasterized technique, because the mirrors are reflecting objects that are behind the camera and outside the frame. So obviously this technique falls apart. Let's activate ray tracing, and you can see now that the results are much better, yet not quite perfect. First, you can notice that the shadows of some objects outside of the camera frustum are curled in the mirrors. You can fix this by adding a ray tracing settings override and activating the extended shadow culling. You will also notice that the second bounce in the mirror isn't quite correct or low res. This is because we are only using one bounce at the moment, and the system will fall back to the local baked reflection probes, which are very low res in this example. To fix this, I'll simply increase the number of bounces to 2, 3, and 4 bounces. You need to be very careful with this number, as the performance cost can be incredibly high. Usually, 1 or 2 bounces will provide good enough results, especially if you have carefully placed reflection probes in your scene. But there is no denying that playing with mirrors is really fun for a moment. One of the most impressive ray-traced effects is the global illumination. Again, I'm going to add the corresponding override to my global volume. By the way, in case you don't see the effect immediately, it could be because your default frame settings for your cameras aren't set to render the effect, so make sure you tick this box. In addition, make sure the materials in your scene are set to receive SSR and SSGI. Depending on your scene setup, you might notice at first that the Raytrace GI is lacking some intensity when compared to light maps. Like with the Raytrace reflection effects I showcased previously, you can avoid this by increasing the clamp value to ensure that rays are able to return higher intensities of lights. Of course, doing so might also increase the amount of noise in the signal. However, we'll be able to easily tune this with the amount of samples later. Due to the way Unity handles directional shadows, you might encounter light leaking in darker parts of your level, depending on the camera position. Again, we can fix this easily by adding a Raytrace settings override and making sure that the directional light fallback is set to 0. If you're already familiar with offline light baking and rendering, you certainly know that increasing the number of samples and bounces will yield better results for light diffusion. It's the same here for ray tracing. Let's increase the number of bounces to 2, and then push the sample count to 3, and then 4, and now you can see the results are very close to the bakelite maps. For reference, the bakelite maps in this scene use up to 6 bounces, but take around 3 minutes to render. Also, one big advantage of ray tracing is that we're getting per pixel lighting, whereas with light maps, we are tied to a certain texel resolution. So far, I've been using the quality mode for the Raytrace GI. This mode, however, is more geared toward very high-end hardware and visualization, and it isn't really frame rate friendly. This is why, for high frame rate applications, like games, we also provide a performance mode. In this mode, there will be only one single bounce and one sample. So obviously, for interior scenes that require a lot of multi-bounce indirect lighting to look photorealistic, it can be a limiting factor. However, we'll see in a couple of minutes that for outdoor lighting, the performance mode will be more than adequate. To showcase the Raytrace GI, let's shine a very powerful spotlight at 20,000 candelas towards the recessed ceiling. Currently, the RTGI is disabled, and because I didn't rebake the scene, the spotlight doesn't produce any indirect lighting. So let's turn on the RTGI again, and now you can see that the lighting will correctly bounce and update in real time as I move the spotlight. I can also change its color, and it will update the lighting over multiple frames. This is a truly interactive way to work, and instead of spending hours waiting for bakes to finish, you can just focus on the lighting and your materials and get immediate high-quality results. I can also change the color of the marble floor, and thanks to the Raytrace Reflections and GI, the lighting will bounce in the entire environment. The same goes for the emissive stripe by the wall. I can reduce the intensity from 400 nits to 40 nits, and the illumination will update accordingly. Of course, depending on your frame rate, these updates can take some time to propagate. Therefore, it's important that you keep an eye on the number of samples and bounces you use in case you need snappy updates. Let's have a look at the second room now. Because this area is mostly lit by a small opening in the ceiling, we need to increase the number of samples to get great illumination in this room. If I disable the denoiser, you can see how the samples are generated. Switching to the indirect diffuse lighting debug view will make the generated lighting even more evident. Once again, you can see how important the denoising phase and the temporal accumulation are in order to smooth the lighting over time. To increase performance, you can also choose to halve the resolution of the denoising pass. As a consequence, you might need to increase the filter radius of the denoising. In any case, with 8 samples and only 1 bounce, you can get very similar results to Lightmap, with the advantage of getting per pixel GI rather than depending on the texel resolution of your light maps. As I mentioned previously, switching to the performance mode that only offers 1 bounce and 1 sample won't lead to great results in this area, because it doesn't receive much direct lighting. Now, let's go to the first room. Because this area receives such a large amount of direct light, you don't need a large number of samples or many bounces to get near perfect results. As you can see, switching between light maps and Raytrace GI doesn't display any particular differences, and the mainstream audience won't be able to tell the difference. Even with just one single sample, results remain very good. This is why switching to the performance mode in this case is now an acceptable solution, especially for games. This makes the performance mode very suitable for outdoor environments that are largely lit by a directional light. Whereas the quality mode could be kept for interiors or areas with more occlusion that require more samples and bounces. Next on our list is Raytrace Shadows. Let's hide our ceiling lamps and use a single point light. You might know that in real-time applications, shadow maps are widely used. In short, shadow maps are depth textures rendered from the perspective of the lights. However, their filtering is a complex subject. Out of the box, Hdrp provides already amazing filtering quality with percentage closer soft shadows, or PCSS for short. This simulates the natural softness of shadows while ensuring they remain sharp near the shadow casters, like in real life. However, this effect is fairly expensive, and for mainstream hardware, you might want to stick to the medium filtering quality instead. With that lower filtering quality, you can see that we are now back to a video gamey look for the shadows, and no matter their distance to the shadow casters, the blurriness of the shadows will remain constant. Now, thanks to the Raytrace Shadows, we offer a fairly cheap alternative while maximizing the visual quality. The pixel on screen will cast a ray towards the light and generate a shadow value depending on the occluders between the light and the receiver. As you can see, the shadows maintain their sharpness close to the shadow casters, while being very smooth as the distance between the caster and the receiver increases. As usual, you can also increase the radius of the analytical light source, and the bigger the source, the more diffused the shadows, exactly like in real life. One great feature offered by Hdrp is the ability to generate semi-transparent colored shadows. Let's drop the same coffee table in the arena. First, we need to make sure the glass casts shadows, and all the LUTs preferably. Enabling transparent colored shadows is done in the Lights Inspector. Know, however, that this effect only works with directional lights at the moment. Then it is just a matter of changing the transmittance color of the material, and the shadows will be tinted accordingly. And to change the opacity of the glass, I simply need to update the base map or color of the surface. This kind of effect is quite a novelty for real-time rendering, because traditionally, the old-school shadow map technique was just a binary approach to shadowing. Either you got fully opaque shadows, or no shadows at all. Now, thanks to Hdrp, you can simulate the shadowing of all your transparent materials in a physical-based manner. Let's go all in, with all ray tracing effects active at once. I'm going to drop a car in the scene and see the kind of results that you can expect with Hdrp. So obviously, thanks to the Raytrace Reflections, you'll immediately get great realistic reflections out of the box. For instance, areas that are typically a nightmare with rasterized techniques like the halo wheels and the underside of the car are looking great with ray tracing. Also, you can naturally get ray trace reflections on transparent materials like the windshield. And of course, the ray trace reflections work as well inside the car. You can see parts of the dashboard reflected onto the windshield. With all effects enabled, you can also notice that the lighting is very robust inside the car, without any light leaking. Now for comparison, let's turn off the ray tracing reflections and GI, and as you can see, the car just inherits the lighting from the arena, but the car doesn't reflect or occlude itself. That's why the inner part of the car will just reflect the sky and therefore look very bright. Without ray tracing, you would have to place many reflection probes inside and outside the car, as well as bake the lighting with light maps and light probes, and this process can take several minutes, if not hours sometimes. So again, you can see why ray tracing offers a little revolution for the lighting setup of your small and medium-sized assets. Just drop them in the scene, and they will provide great lighting immediately, without any particular setup. Let's now place the car inside the third room of this template. All the ray tracing effects are currently disabled, and out of the box, the car will appear as floating in the environment and won't produce any occlusion. First, let's enable the Ray Trace GI. I'm not quite satisfied with the indirect lighting there. It's lacking in intensity, so I'll increase the number of bounces to get softer and more correct results. At the moment, the reflections are handled by the baked reflection probes. This means the car isn't reflected in the environment, and the car doesn't reflect itself, because I didn't rebake my reflection probes. Let's activate the Raytrace Reflections. Now you can see correct occlusion under the car. The paint looks more convincing, and alloy wheels get great specular occlusion, and the disc brakes, for instance, don't look as if they are glowing anymore. Finally, I can activate the Raytraced Ambient Occlusion, which will give me a way more correct approximation of the indirect occlusion in the scene, especially under the car. If I turn off all the ray-traced effects, you can appreciate the difference. You could indeed spend a lot of time generating light maps and placing reflection probes very carefully around the car to get fairly similar results. However, the lighting would only be valid for this specific area. So if the car was able to move around, the baked diffuse and specular lighting would quickly become incorrect. This is why ray tracing is so useful, both in terms of visual quality and iteration time. Finally, you also need to understand that having all ray tracing effects active at once is very expensive. Depending on your hardware, you might have to dial down certain effects, if not most of them. For instance, for high frame rate scenarios like games, you could decide to only use the cheaper ray-traced AO and shadows, and stick to baked GI and reflections for the rest of the lighting, because ray-traced reflections and GI still remain fairly expensive effects. The last effect I will talk about in this session is path tracing, which is a unified form of ray tracing using a more brute force approach. Activating path tracing is also done with the volume system. You just need to add an override. The way it works is quite simple. Rays are shot from the camera, and whenever they hit a surface, we shoot yet other rays at nearby surfaces and sources of lights in the light cluster. The journey of the rays between the lights and the camera is called a path, hence the name path tracing. The main downside of this technique is obviously noise. However, we can accumulate samples over time to create a noise-free image. You can actually see a progress bar at the bottom indicating the number of frames that have been so far accumulated. The advantage of path tracing over the other ray tracing methods shown in this session is that it provides a unified process to generate all the lighting, such as shadows, reflections, refraction, and global illumination. Let's add our car back to appreciate the complexity of the lighting. You can control the depth of the path. With a depth of 1, you will only get direct lighting, which means no indirect lighting at all. You can then increase the maximum depth to get softer indirect lighting. For darker interiors, you will probably need a fairly high depth value to capture enough indirect lighting, and therefore it can take a longer time for the image to converge. Of course, it means this method cannot be used for real-time applications just yet, as it generally takes several seconds to generate clean frames. If I then go outside, given there is a lot more direct light, the image will converge extremely fast. And you can get beautiful lighting with soft shadows and glossy reflections in a matter of seconds. By the way, you'll notice that the decals aren't supported in this mode. Remember that the ray tracing in Unity is still in preview. You don't need to place any specific lighting objects such as light probes or reflection probes anymore. You just need a sunlight and local artificial lights. Before I end this session, let's go through the different methods available to generate the lighting. First, we have path tracing. Then I have the 4 ray trace techniques I presented earlier, which are Raytrace Shadows, Ambient Occlusion, Reflection, and GI. Finally, if I turn off the ray tracing, I am left with the old school rasterized effects using baked light maps, light probes, and reflection probes. Let's check the first room of the template again and do the same exercise. Here's the path traced image, then the version with Raytrace GI, Reflection, and Ambient Occlusion, and finally the rasterized one with baked indirect lighting and reflection probes and screen space reflections. And we've reached the end of this webinar. I really hope you've enjoyed this deep dive into Unity's ray tracing capabilities, and hopefully you've learned a few things and are now aware of the amazing graphics you can create with the high-definition render pipeline. If you want to experiment with HDRP and this exact level I've used in this presentation, simply download the latest release of Unity and you'll be ready to explore the world of ray tracing in no time by following the instructions in this session. And in case you are stuck and need more information about these functionalities, don't forget to look for the HDRP documentation online and consult the pages related to ray tracing. Make sure you select the right HDRP version, by the way. For instance, have a look at the recursive materials and how they can help improve the rendering of small objects that require several bounces to produce convincing reflections and refraction. The ray tracing in HDRP is still in preview, so you can expect further improvements and bug fixes in the next releases of HDRP, so stay tuned. Again, thank you for watching, and if you liked what you just saw, please let us know. Take care and goodbye.